Our next presentation is Enhanced Autonomy and Efficiency for Lunar Exploration using new FDIR and multicore. This will be with Laurentiu Nicolae is presenting.
Can you guys hear me?
Yes, we can hear you.
Great.
Go ahead.
Okay, I'll go to full screen. I hope you can also see my screen properly. Right, so good morning to all. My name is Laurentiu Nicolae, and today I'll talk to you about enhanced autonomy and efficiency for lunar exploration using new FDIR and multicore. A few words about the authors. Myself, I'm a systems engineer in moon payloads development at the European Space Agency in the Netherlands, and I support a number of moon-related missions and payloads. My colleague, Javier Fernandez Salgado, is a flight software engineer also at the European Space Agency. He's also supporting a number of space missions and also a number of them related to moon exploration. Currently, there is a notable resurgence in the interest surrounding lunar surface exploration, distinguishing itself from the endeavors of the 1960s by the active participation of commercial entities. The graph on the screen is actually incomplete as more commercial missions are in planning today. A primary justification for contemporary lunar exploration lies in the discovery of valuable resources located at the South Pole, particularly the presence of water ice reserves. Effective prospecting of this region requires systems capable of sustained operations over extended periods of time, spanning multiple lunar days, amidst constrained communications and limited human intervention. This emphasis on autonomy is derived from the challenges associated with communications, but also with the lunar night. Communications with assets on the moon's surface requires networks of ground stations spread on various locations on Earth. Moreover, the data volumes are generally low, determined by communication blackouts and delays. Hence, limited transfers take place. The lunar night also lasts approximately 14 Earth days, during which temperatures drop dramatically and solar power assets go in darkness. This poses significant challenges for communication and power supplies. Solar powered equipment must rely on battery reserve to survive the cold and dark night, limiting operational capabilities and communication windows. Consequently, the imperative lies in the development of a robust fall detection, isolation, and recovery subsystem integrated with a high throughput processing capability in order to compensate for a limited interaction with ground operators. Drawing from that assessment, we could define a number of high-level requirements focused on a generic surface payload. For the purpose of this presentation, only a few requirements are defined, which are relevant for the autonomy area. However, many others can be put forward. The first one, the payload deployed on the lunar surface shall possess the necessary functionality to execute its designated mission continuously throughout extended durations, encompassing the lunar night cycle. The imperative to acquire comprehensive data mandates that forthcoming payloads operate continuously for prolonged periods of time, ensuring the maximal acquisition of data over time. The second one, the surface payload must exhibit a high level of autonomy, enabling independent operation and decision-making capabilities. Throughout the mission execution, intermittent and unpredictable communication disruptions may occur. Consequently, the payload must possess the capability to execute its mission reliably and deterministically, even in the absence of continuous communication. And the third one, the surface payload shall autonomously adapt its behavior in real time based on incoming data, sensor readings, and situational awareness to optimize mission performance and ensure mission success. By continuously analyzing data and sensor readings, the payload can make informed decisions to optimize resource utilization and task prioritization. Real-time adaptation allows the payload to adjust its operations dynamically, maximizing and achieving the mission objectives. From the system requirements, we can derive some FDIR specific requirements that shall enable a high degree of autonomy for the payload. One of them is R4. Upon detection of a fault, the payload shall initiate an automated isolation process to identify the root cause and localize the affected system or component. As a justification, the swift identification and isolation of faults are crucial for minimizing downtime and ensuring the payload's continuous operation. By automating this process, the payload can rapidly address issues without relying on human intervention. Next one, upon successful isolation, the payload shall implement automated recovery procedures to mitigate the impact of the fault and restore normal operations. This is justified by the fact that automated recovery procedures help minimize disruptions to operations by swiftly restoring normal functionality after a fault has been isolated. This ensures that the payload can continue its mission with minimal downtime. And the last one, the FDIR subsystem shall integrate with the payload's autonomous decision-making algorithms to dynamically adjust operations and adapt to challenging and changing conditions in response to detected faults. By integrating with autonomous decision-making algorithms, the FDIR system can dynamically adjust operations in real time based on detected faults. This capability allows the payload to adapt swiftly to changing conditions, ensuring continued functionality and mission success. For the definition of the FDIR concept, we have used SwRI, which stands for Space Avionics Open Interface Architecture, which is a European initiative to federate the space avionics community and to work together in order to improve the way that the European space community builds avionics subsystems. And from the FDIR, we could trace a number of statements. One of them is a general rule of thumb is to place the FDIR as close as possible to the potential source of the risk that it tries to mitigate. This is typically determined by whatever component has the capability to detect the source of the risk. Operational needs should drive FDIR architecture, for example, deciding whether or not fail-safe or safe operational is implemented. In any case, FDIR should always report mitigation actions taken. FDIR relies on three basic architectural steps to achieve its goals. The ability to notice that something bad has happened, fault or failure detection, depending on whether we can observe the event itself or observe by sampling the change in the system or component state. The ability to isolate the fault or failure. This has two aspects. One, the system's ability to uniquely identify the fault or failure from the changes witnessed in the observables, and two, to prevent the fault or failure from propagating and causing other faults to occur as a knock-on effect. The third and final step is to recover in time from the fault or failure. This can entail many things. For example, simply do nothing and wait for ground to intervene, take control, and resolve the issue. Another approach might be to passivate the component that is at fault and then wait for ground, or some onboard autonomy function can be started that tries to resolve the failure or fault. The result of the concept definition is basically the following building blocks for the FDIR. And we have defined a number of them. The first one, the situational awareness module, a component designed to gather, process, and analyze data from the various sources to provide a comprehensive understanding of the system's operational environment. The primary function is to monitor the status of the external environment in real time. The internal monitoring module, a component dedicated to the continuous monitoring and analysis of the internal state of the system or subsystem it is integrated with. The primary function is to detect deviations from normal operations, identify faults or failures within the system, and provide necessary information for fault isolation and recovery processes. The isolation module, a component responsible for determining the root cause of detected faults or anomalies and isolating the affected components or subsystems to prevent the fault from propagating further and causing system-wide failures. The primary function is to facilitate the localization of faults and enable targeted corrective actions. And then the recovery module, a component responsible for implementing strategies and procedures to restore the normal operations after a fault or anomaly has been detected and isolated. The primary function is to execute corrective actions to mitigate the effects of faults and bring the system back to a functional state. Internal resources module a component designated to manage and optimize the allocation of internal resources within a system or subsystem. The primary function is to ensure efficient utilization of available resources while maintaining system performance and reliability. Considering the previous building blocks, we can create a global FDIR architecture for a generic system to be used on the moon surface. As you can see here, the situational awareness module feeds the internal monitoring module with data from sensors and other sensing means. The internal monitoring module acts as a master element taking into account the external data, but also internal data from the various internal sensors. And when a failure is detected, the isolation module assesses the data and evaluates the level at which the failure should be recovered. With this information, the recovery module checks if the recovery action can be implemented based on the input from the internal resources module. The subsequent recovery action can be implemented at system level, but in most cases it will be done at a lower level depending on the needs. And you can see that this FDIR architecture aligns with the technologies available at the European Space Agency. The architecture involves two technologies. Firstly, the situational awareness module on the top. This module leverages advanced machine learning algorithms to enhance the detection of complex patterns. Although this technology is still in its early stages of maturity, we are actively exploring how to integrate machine learning into space applications. We are also identifying frameworks that can seamlessly fit into our target systems and surface and software toolchains. And secondly, the real-time operating systems and hypervisor on the bottom. With the high technology readiness levels, these technologies are important for isolating faults and enabling recovery. They are rated with a criticality level B for our targets, which includes dual-core Leon 3, quad-core Leon 4, and octa-core Leon 5 processor. And at agency level, we are gradually transitioning to RISC-V compatible systems where we are building a robust software ecosystem. In addition, we are exploring activities aimed at identifying and implementing mitigation strategies for inter-core interferences. Our objective is to leverage these harder solutions to ensure compliance with real-time constraints and to address these adverse effects. On this slide, you can see the two hardware solutions considered currently by the European Space Agency, both of them courtesy of front-grade Geissler. The first one is the established GR740 device, which is a radiation-hardened system on chip, featuring a quad-core fault-tolerant Leon 4 processor with an 8-port spacer router suitable for both symmetric and asymmetric multiprocessing. And currently in development, the GR765, the next generation radiation-hardened fault-tolerant octa-core system on chip, with the option to select between Leon 5 and Noel 5 RISC-V processor cores available, but suitable for both symmetric and asymmetric multiprocessing. Having discussed all of these items, now it's time to apply the concept and architecture and the hardware solution to concrete cases. And for that, we have chosen two payloads for this. Both of them will be surface payloads on the moon. The first one is Prospect. Prospect is a comprehensive payload package developed by the European Space Agency, which will support the extraction and analysis of lunar surface and subsurface samples, as well as the acquisition of data from additional environmental sensors. The Prospect package consists of two sub-assemblies, the Proceed drill, which supports the acquisition of soil samples from the lunar subsurface up to a depth of 1 meter. Proceed consists of a drill and positioner, whose main task is the sample collection, transportation, and delivery of collected samples to PROSPA, and the control electronics unit, which houses the electronics controlling the whole package. The second subassembly is the PROSPA instrument, which allows the analysis of acquired samples by means of volatile extraction, gas processing, and mass spectrometry techniques. PROSPA is composed of two physical units, the solid inlet system that contains a number of single-use sample ovens on a rotary carousel, together with a sample imager, SAMCAM, and an oven sealing mechanism with a miniaturized analytical package, incorporating elements for volatile processing, 2 mass spectrometers, and associated ancillary and control systems. The key objective of Prospect is the detection and characterization in surface and subsurface samples. In this context, the preservation of volatiles in acquired samples up to the analysis stage is among the main challenges for Prospect. The whole package will be hosted on a NASA CLIPS mission that will last around 10 days on the moon surface. For the current mission, frequent interaction with ground is required in order to ensure a safe operation of the payload. This is driven by the complexity of the payload, but also because of the limited computational capability currently in the system, which is a single core processor. And in order to maximize the science return, operations will be executed in a partially parallel manner, which will add to the overall complexity of the mission. In order to extend the autonomy of Prospect, a multi-core solution can be implemented together with some new FDIR building blocks. By implementing this FDIR architecture, the payload will gain more autonomy, including operational time. In this case, in the case of PROSEED and PROSPA, failure recovery and isolation can be mitigated by restarting specific partition. This approach allows for targeted intervention without affecting the entire system, thereby enhancing system resilience and reducing downtime. Utilizing a multi-core system with a hypervisor will significantly enhance isolation and recovery modules. And software can manage partitions more effectively compared to single-core federated systems, which sometimes require a power cycle. And I would like to quickly go through a small diagram that I will put on the screen. So here you see the application of this FDIR architecture on the existing Prospect payload. For example, if we get an error in the drill and positioner, this will be raised by the monitoring module, which will basically monitor all the time the status. And as a result, this will be further sent to the isolation module that will try to isolate the failure so that the other part of Prospect, which is PROSPA, will continue to perform its task uninterrupted. The isolation module will basically stop PROSEED, and then determined by the internal resources state, it will feed the recovery module. Sorry, excuse me. There is something bad that has happened. There you go. So the recovery module will take this resources status and determine if we can implement the recovery module. And if this is possible, it will start the recovery actions. And as I said, because we would like to implement a multi-core solution, we are basically separating the two subsystems so that one of them can continue its operation, thereby maximizing the overall data that is acquired during the mission. And now we'll come back to my presentation. And the next use case is basically a payload that is under development by the European Space Agency, the Surface Deployed Package, which will support the scientific analysis of the moon surface environment. The package will consist on a surface module, which will host its own solar panels and batteries, an electronics module, and a number of science instruments that will measure various environmental parameters. The package will be designed to be deployed by astronauts, and the surface phase of the mission shall last around 2 Earth years. For a potential mission, the package must be as autonomous as possible, since it shall operate during the lunar night and shall maximize the operation of the science instruments. Moreover, the package must also monitor its internal resources, first to ensure nominal operations of the instruments, but also to guarantee the execution of recovery procedures in case of failures. Similar to Prospect, a multi-core solution is highly advisable in order to extend the autonomy of the package. Moreover, the FDIR module shall provide a high degree of robustness. And as you can see here, the situational awareness module shall be implemented as a bespoke module integrating external sensors. For the internal monitoring module, a dedicated core shall be assigned, since the module shall be always operational. The isolation module can be assigned to a core, but only as a sporadic task. And the internal resources module shall have a dedicated core in order to extend the autonomy of the overall system, and it shall also monitor the resources status of the science instruments. To conclude, I would like to mention that in the new age of the exploration of the moon, more autonomy is required for performing longer-lasting surface missions. In order to achieve this objective, specific requirements shall be defined and flown down to the FDIR elements, but also to the hardware and software elements. In realizing these objectives, it becomes imperative to tailor the FDIR building blocks to the unique demands of each mission, fostering a close cooperation between mission requirements and autonomous capabilities. And furthermore, the adoption of multi-core hardware emerges as a prerequisite, facilitating the computational capability needed to accommodate the escalating demands of autonomous systems. So thank you very much for your attention. And if you have questions, I would gladly like to ask them. In case I cannot manage that, feel free to contact me on LinkedIn, or we can take the questions offline after. Thank you.